Okay, it's about the time. I'm going to go ahead and get this started. Okay, so we can remember that we continue the same kind of a discussion that we had on uh, last Thursday. Last Thursday we finished, completed last week. We finished chapter 9. In chapter 9, we are mainly uh, talking about that estimates of the parameters. The main parameters you saw that that we were talking about the population mean. The population mean cannot be evaluated, accessed, computed. What we did was that we were looking for an estimate for that one. Not only that, beyond that point, that what we did was that that point estimate not be counted only for one sample. Instead of picking one sample, what we did was we hypothetically assumed that we were that generating several samples, many samples. That you're not going to do that one practically. There's no way that you cannot go ahead and then pick the several samples, many samples, million samples, or there are thousand samples. There's no such thing. What we did was that we simulated. You saw that one, and with the aid of the simulation, we just talk about the something called sampling distribution. Sampling distribution is nothing but the the distribution of nothing but the distribution of uh, sample estimate. That's a distribution of estimate. You can remember that estimate gonna be fitting into a distribution for certain reason. Why it gonna fit in into a distribution? Because we think that if you're gonna pick different samples, different samples. Okay, okay, I'm gonna wait a little bit. I think Grace, she's joining. Hi, Grace. Good evening. And then I just started, and then I was talking about that I'm going to continue the same discussion that we had on last Thursday plus that whole last week. Last week we covered chapter 9. In chapter 9 we were talking about the distributions, some concept called the distribution. Before that in chapter 8 we were talking about kind of like a estimate. So estimate means like a mainly we focus on that population mean. Population mean cannot be in the event of that population mean cannot be accessed, evaluated, or computed. What we did was we pick a sample and then we calculated the sample mean. Okay. Then later on, what we did was that we know that we had only one sample. With the aid of that sample, we evaluated sample mean. Then we can say that, okay, this would be the best estimate for the population mean. But that's not the proper way of doing that. What we did was that we are supposed to pick so many sample, many sample, and then evaluate the sample means and then make the conclusion about the population mean. In such a when we were in the middle of that picking up the samples, we just came across something called that the sampling distribution. Sampling distribution is nothing but the distribution of the sample means. Sample means because the sample means gonna differ from the sample to sample. That the varying of the values from sample to sample of the sample mean constitute as some kind of a random variable that can be fitted into a certain distribution. When you have like a variable can be put into like a condensed form, and then you can easily draw the histogram. With the aid of histogram, we can get the distribution. Distribution is nothing but that a smooth curve scheme in the top of the histogram. So you saw that one. In that discussion, we mainly we're not gonna go ahead and pick the samples. So many samples. We don't do that one. We cannot pick this million sample, billion sample. We cannot. What we did was, even though that we say that we are not happy with the like making inferences with the one sample and then thinking about getting more samples, that sample are not practically observed. What we did was they were theoretically, or that using our programming, we just generate, or we call the simulated. We simulated samples and then we calculated their sample means. In that discussion, mainly that you saw that y bar is a sample mean. Sample mean y bar has like a distribution called the sampling distribution. Before that y come to y bar, you have in the some kind of a, for one sample you draw the histogram called the sample distribution. Even before that one, that you can think of that if this sample is like a certain shape, has a like a, when you draw the distribution, it has a certain shape. By looking at the shape of the sample distribution, you can just come to a conclusion and say, hey, this distribution or the data has been derived from or the extracted from some kind of a population distribution which has this kind of a shape. In the very beginning, for mathematical tractability, we thought that it's going to be bell-shaped and normally distributed. That kind of a discussion we built up. If I recap what we did little bit before we get into the today's topic, today's topic is the same discussion that we had for the chapter 9 is an extension. Extension means like in chapter 9 we were talking about just a one estimate. We talk about one estimate, one y bar, and then we talk about several y bar as well, and then we condense and say they can be distributed according to certain distribution, which is sampling distribution of y bar. Now, in the backward process, you can remember we were thinking about the forward process and the backward process, two processes about our estimate. Our estimate means y bar. When y bar we were talking about, we were in the backward process. That's where we stopped last time. We were thinking this y bar would be by how much differ from the true mean. Sample mean is how much that differ from that population mean. That difference is we call the error, or the later on we can say that maximum such kind of error called the margin of error. If the error that incurred by estimating any parameter, in that case the population mean, it's called the error. The maximum value of that one is called the margin of error. Okay. Before I'm going to get into that one, I want to just recap what we had been doing last week. So then you get a clear idea what we are heading towards. Okay. Let's see. Okay. Come on. Okay. Okay, I'm gonna share. Sorry, I'm gonna share this other screen. Okay. So I'm using this book. Okay. Yeah. Yeah. Before come to this one, I wanna tell you something. This is what. This is where we found that. This is everything related to our that regression or our models, in which that we were using some kind of a model to explain that variation of y with respect to another explanatory variable. In that discussion, you saw that how we did things. Okay. Look at that. This is what I was talking about. We have estimates of our models. Let's look at what are the models that we were talking about here. You can remember the first model, nothing but the null model. See, null model. You can remember how we wrote the null model, y equals y bar plus error, or y hat plus error, or b naught plus error. That's the same thing. See, that's the same thing. See, y has been explained, especially that, let's say for instance, thumb length has been explained by its own mean. That's the mean I'm talking about. Because this mean, what we did was, instead of picking up one y, see, y bar is my estimate. See, here y hat or y bar or b naught is our estimate. This is based on one sample. But what we did was that we were, instead of picking from one sample, we were trying to get the y bars from several samples by through the simulation process. This is what I'm talking about. See, simulation process. See, with the aid of simulation process, we thought that data coming from some kind of a normal distribution, and we had 157. We get the mean, we put the mean, standard deviation, we generated, and we found the mean, and we did this 1,000 times. See, then we drew the histogram. We can put the smooth curve on top of that using this one with the labels like that. See? Or it has another way of getting this done. Instead of using this, assuming that your population distribution of thumb lengths are normally distributed, you can think about they are can be you get that you it's called a bootstrap. Bootstrap means like whatever that you got over here, that the sample, you have the sample. What are you going to do? You resample that one. From the sample, but you have a sample, you pick 157, see? Resampling. You're going to pick resampling, see? Resample. You use the same sample again and again and again and again and recycle it. See? You recycle it. See? You go to the fingers data, thumb length. Can you remember it has not so many, see? 157, you see? You pick 157, see? And then resample, see? What you're gonna do, that you have a sample. That sample data points, okay? You're gonna pick 157 data points. We can remember that fingers data, no? Tiny fingers data, we have like a 6 data points. The other one has like 157, see? And then we're going to find the mean, and then we redo that one again and again. That's called the bootstrapping. I'm going to get into that one later on. But anyhow, what I'm trying to say that this is where this is sampling distribution, simulator sampling distribution. So this, when we have our estimate, we say that this particular estimate, y bar or y hat or b naught, distributed, you know this sign, this tilde means is distributed according to certain distribution. Can you remember this estimate? See? Certain distribution with its mean. How do you denote by the mean? Mu y bar, see? Mu y bar. And standard deviation, sigma y bar, see? That's what we were talking about the last time. That y bar is coming from that null model, see? Because it's going to be like that for a certain reason. You know that if you have a population here, from the population, if you pick a sample, see, sample 1, okay, of size n equals 157, let's say our thumb length here, where y equals thumb length, okay, thumb length. See, if you measure that one, that's your y bar 1. If you get another one, sample 2 of same size n equals 157, but if you get from this population, if you get the sample of 157, see, that would generate this one. I'm not talking about that y bar and y2 that we generated, but y bar, we have at least one sample in our hand, okay? That's not enough to do this discussion. Because if you have like 1,000 sample, let's say that sample 1,000 of the same size n equals 157, see? then its mean would be y bar 1000. See? So these numbers, whatever the numbers you're going to get for y bar 1, y2 bar, y bar, 1000 y bar, they differ from each other. That's why they constitute a random variable. Constitute a random variable in which in return distributed according to certain distribution, just distributed according to certain distribution with mean mu y bar and standard deviation sigma y bar. It happens all the time. See, look at the y bar is nothing but your estimate, something you're interested in. The population maybe has like so many students, maybe 10,000 students. Out of 10,000 students, you have picked only 157 students and check that one. You have one sample in hand, but that's not the case. One sample is not enough for you to make a conclusion about at the end of the day. Then you are thinking about picking so many samples, but you don't do that one as well. What you're gonna do, you're gonna simulate and see how they're gonna fit in into. They have built up some kind of a model theoretically and say, as if okay, like that. If we're gonna that generate 1,000 samples, out of this sample, if we have generated 1,000 samples, their mean would have been distributed according to certain distribution. That theory has already built up. So because of that reason, with the we're gonna say that they fit in into certain distribution. That's why we have y bar hat, y hat, b naughts distributed according to certain distribution. So let's go to the second one, second model. Second model you can remember. Second model is a group model. Can you remember? The group model, or we can say categorical model. In categorical model, you can remember y equals b naught plus b1x plus c. Okay, and you can remember b naught is nothing but y value when x equals 0. Y when x equals 0. Y value, that means thumb length for male or female. It's based on the gender, categorical. Can you remember categorical? Okay, x0 represent one class of that particular category. Okay, that's also b naught. But here again, b naught gonna be not only one. B naught, there are so many B naughts, because if you pick another sample, whatever the sample you have in your hand, you can calculate B naught. Our program gonna calculate the B naught and give you the value. That's not what it's not enough for us to make a conclusion about the beta naught. Can you remember? Its counterpart beta naught. It's not enough. That's why we pick so many samples, 1,000 samples. If you pick 1,000 samples, as an example, I pick 1,000, but if you pick 1,000 samples, their B naughts not going to be the same. They're going to differ. Like this picture. See, same picture like this. See, they're going to change from the sample to sample. See, B naught going to change. Okay, therefore, it's going to distribute according to certain distribution. It's also according to certain distribution. With what? Mean, I would say mu of B naught. See, put like that. And standard deviation of sigma of B naught. See, sigma of B naught. See, like that. You see, that's how we're gonna say is distributed. This tilde means distributed. That's like a concept. Okay, distributed. There's certain distribution. We don't know what kind of a distribution, how it looks like. We can say like that. And on the other hand, B1 is what? B1 is y x equals 1 minus y value when x equals 0. Can you remember the gap between the male and female? Like that. This also according to a certain distribution, distributed according to certain distribution, with mean mu b1 and standard deviation mu sigma b1. See, like that. Like that. That means that if you, from the population, if you pick a sample, see, sample 1 of size 157, and if you calculate B naught and B1, I can say this is B11, B11, see, B0, B1, B01, B1. If you go to the second one, sample 2 of same size 157, then you're going to have a B0 second one, B1 second one. I put it's like a superscript for you to distinguish from the. Then you're going to go to the 1000 sample 1000 of size same thing 157. If you calculate the B0 for this guy 1001 and the B1 for the 1000 sample, those values not going to be the same. That's why they distributed according to, they constitute a random variable again, like earlier, see, constitute a random variable which in return distribute according to certain distribution with means mu b0 and mu b1 and standard deviations sigma b0 and sigma b1 respectively. Okay, that's the b1. Okay, this is b0. I'm going to write here sigma b0 and sigma b1. See? That's why we're going to say that distributed. That's the discussion that's going on over here. Okay, so the third one, let's go to third model. Third model is, you know, the regression model. Regression model, you know how it's been written, y equals b0 plus, very similar to what we had on the other page, but only difference, you know how they differ from each other. Earlier your x would be an explanatory variable, sorry, that's called the explanatory variable. This x explanatory variable is a categorical variable. It's a categorical explanatory variable. But on this regression model, you have a continuous, see, or quantitative or numerical explanatory variable here in x. That's how they differ from each other. In this case, you can remember your b0, b1. Can you remember how they calculate b1? We don't do this one. I'm going to write that x minus x bar, y minus y bar, and take the difference and then multiply together and divided by x minus x bar, whole thing squared. This is what the program does for us. We don't have to calculate it even. But this is also distributed according to a different distribution, because you're going to have a different b1s with mean mu b1. That's how we're going to denote standard deviation mu sigma b1. See, sigma b1. Then we go to the b0, its counterpart b0. So y bar minus b1 times x, also distributed according to certain distribution. We don't know what distribution. With a mean equals mu b0, comma, standard deviation sigma b0. See? Right. That's where we were the last time. We had an estimate. These are estimates. Remember, these are estimates. Estimates. Because you cannot access beta naught and beta. These are estimates based on the samples or sample. A sample or sample. See? So estimate. See? Those are estimates. Those estimates gonna be y bar. Sometimes estimates gonna be, see, based on your model. See? In the first model, your estimate would be what? Y bar. Certain distribution. We will talk about this one in large scale. See? Y bar in the first model. If you go to second model, you are interested in b0. This is nothing but is again, if I write this one very clearly, this one also y bar. This one also y bar. See, if I write this one in another form, only this part is nothing but y bar of female. Can you remember male, female? Then this one is nothing but Y bar of male, Y bar of female of the thumb length. Can you remember? You can remember every time we were taking into account the averages. See, whole discussion has been done through averages. Even over here, look at average gonna come into the picture again. See, somewhere here. See, even on this formula, you see the average. Average playing a very heavy role at the end of the day. That's why we mainly focus on the average in the very beginning. But B0, B1, they are consist of, see, they are made of Y bars and X bars. See, doesn't matter. But we just talk about the estimate. These are estimates. See, B0 and B1 estimate. These are estimates. Those two are estimates. See, estimates. Those are estimates. See, this one, estimate. In another way, I can call that one a point estimate. I prefer to use that word here, point estimate. It's a one estimate only. It's based on your sample, point estimate, based on your sample. Now, in this chapter 10, what we're going to do, that statistician practitioners, they are not happy with only one estimate. They say that give me that not like a one value. They say no, give me like the range of values, range of point estimate, range. Like if you're planning to buy something, you're like let's say if you're gonna buy like a new house, you don't like the exact value of the house. You say that okay, you're gonna say that I'm looking for a house in this range. For your realtor, you're going to tell, okay, I'm looking for the house in this range. Then based on that, whatever the range that you're interested on, whoever the realtor going to go ahead and then look for house that fitting into your range. That's the most advantageous way of that expressing something at the end of the day, rather than giving only one value and say, I really need to buy a house at this only this amount. We don't say like that. Just look for a house in that range. Same way, we give, instead of giving the one estimate, okay, instead of giving one B1, now you might be thinking, no, I was talking about several B1, why he's talking about here B1, so many B1s. No, we know that this is the tricky part here. You have one sample in your hand, empirically, practically, everything based on that one. But then why we have so many samples? No, we didn't pick the sample. We generated sample to fit into our theoretical aspect. That's it. Because in order to that make the conclusion, inferences, and they come up with the exact solution, we do this one theoretically, okay, hypothetically. See, theoretically or hypothetically. But we don't have many samples. We have only one sample. Everything based on that sample. That's why I'm telling that based on that sample, whatever the observed sample is the one you're going to utilize in order to calculate B naught B1. You know that one. In order to calculate B naught and B1 here. In order to calculate B naught or Y bar here. See, that's the one you utilize. That's the one that program's going to utilize. One sample, not many samples. Many samples are coming thinking that as if what's going to happen that instead of picking one sample, if you pick many sample, how it looks like, and then that give us like a very perfect answers at the end of the day. Yes, instead of giving that one based on one sample, if you say that I'm going to give the answer based on many sample, that would give you very exact answer, or that rather than approximate answer, that's going to be very close to the true value. We can make our estimate as close as to the true value or the parameter value when you get the more samples. That's why we pick the more samples, that reason. But you have one estimate. See, you have one B1. You might have a 3 or something like that when you calculate based on the given sample. You can remember that in regression model what we got over here. I think we cannot remember. No? Okay, anyhow, this one we can remember, I think. 65, 62. This one, 62, we got 62 in that thumb example. Okay, 62, that estimate. This estimate 59 and 65, something like that. Okay, so this one, another value. Okay, based on the heights. That time I didn't use the gender, I used the here height, here thumb length, still thumb length, height. In this model, I used thumb length and gender. Okay, here in this model, I used thumb length only. See, thumb length only, and its mean has been utilized to explain its variation. So that's why, as I said earlier, now in this discussion, if you're going to continue the same discussion that we had for the chapter 9, towards this chapter 10 discussion, what we're going to have is that instead of point estimate, we're going to have a whole bunch of estimates called the interval estimate. That's what we call the confidence interval. We are trying to build up interval estimates. Interval estimates. Okay, that's what we are planning to do in this one. Rather than this one, we're going to extend this one to interval estimate. Interval estimates. How do you get the interval estimate? Based on the sampling distribution. See, it seems like this one. You have a parameter. Let's say, for instance, okay, parameter. It's unknown. See, let's say that parameters are, in this discussion, my parameters were mu, beta naught, beta 1. They all are unknown. Those are coming from population. Population. Since they were unknown, you're going to go to what? Estimate. Estimate. They are coming from sample. You have only one sample based on that, and then instead of mu, you're going to have y bar. Instead of b naught, you have b naught. Instead of beta 1, you have b1. See, they are countable. Now what are you going to do? This is point estimate. Now I'm going to go a little bit further down. With the aid of what? Sampling distribution. Sampling distributions. And I'm going to make interval estimates. Interval estimates. Interval estimates. I'm trying to build up interval estimate, not a point estimate. Whole bunch of estimates. How do you do that one? I'm going to call that one confidence interval. I'm going to call that one confidence interval. I'm going to write with this one CI to say confidence interval. Whose confidence interval? Let's say mu's confidence interval. Population means confidence. How do you write that one? I'm going to say y bar minus something called the margin of error, MOE. I'm going to write over here, MOE, margin of error, which is called the maximum error incurred when estimating an unknown parameter. Margin of error is a maximum error. What is the error? You can remember, you have a y bar, you have a mu, that gap, see, gap, you're going to maximize. That's called the margin of error. Okay, that's called the margin of error. Comma, y bar plus margin of error. See, that's called the confidence interval, CI. I'm going to write over here, CI means, CI mu means confidence interval for the population mean. In a similar fashion, you can write that one for confidence interval for beta naught, confidence interval for beta 1 as well. We're gonna, okay. So this is the major part. We don't do anything by hand, but everything can be done by this R programming. So only thing you have to understand what's going behind not the heavy theoretical aspect. Get a rough idea what's going on. See, we leave some space for that to see. We are not interested only in y bar. We say give me a range. This part we call the lower bound. This called the upper bound. See, in another way that this part you can write lower bound, comma upper bound. See, LB means lower bound. This means upper bound. See, upper bound. You're going to give that one as a range. That's what we are trying to do. How we had a population, we go to the sample. With the aid of my sample, whatever I have, I say that this is my y bar, this is my b naught, this is based on observed sample, but this is based on simulated samples. This is based on simulated sample or bootstrap sample. We're going to talk about the bootstrapping. Okay, sampling distribution is created through the bootstrapping or simulation, not from the observing. Observing part is this one. See, to make it clear, see this one. See, and on the other hand, these are unknown, parameters unknown, okay, parameters unknown, these are known, these are known. This is based on observed sample. The sampling distribution based on simulated sample, simulated or bootstrap. We're going to talk about bootstrap samples. See, either way. Observed sample, you're going to utilize and say, hey, I have only one y bar, 62, b naught. In that the second model, that categorical model of b naught is like a 59. The average height of females, 59. Then the 60 b1, average height of males, 65, something like that. 65, I think. Yeah, I can't remember. So like that. In the regression model, again b naught and b1. See, like that. But those are based on that. There's a sample, only one sample. But the sampling distribution not from your sample. No, your sample has to do nothing. Only thing that your sample has to do, we're gonna get its mean and standard deviation to fit in into it, and you're gonna generate the data. So you see, generate data like this. See, if I go back and say that, look at. If I'm gonna show this one, another bootstrap. See, simulated data. See, you believe like your data thumb lengths are bell shape distributed. You're going to generate 157 based on the what? For the mean, you're going to put the mean of the thumb lengths. Mean of the thumb lengths. How do you get the mean of the thumb lengths? You go to thumbstat and then to find the mean, or you're going to find the mean of thumbs. Either way, we discussed this one in several ways, large scale, so many times. So standard here. That's the only place you're going to use your sample to generate the simulated samples. These are simulated samples. With the aid of simulated samples, you're going to calculate their mean, and then with the aid of those means, you draw the histogram. That's called the sampling distribution. We know that one. We did that. See? So that's the same thing I'm trying to say over. But point estimate, no, not based on that one. Then interval estimate is a combo. It's based on the observed sample as well as the simulated or the bootstrap sample. They both should be taken into account in order to give the confidence interval, which is the whole bar, is a range of point estimate. This is nothing but the range of point estimate. Whatever the estimate that you are interested on, point estimates. Okay, range of point estimate. But how do you get that one? With the aid of point estimate, which is based on observed sample and bootstrap or simulated sample, because you need the sampling distribution in order to make the confidence interval or the range. Range is coming from the sampling distribution, not only from this guy. See? This guy here, see, only here. See? So in a similar fashion, I can write the confidence interval on this page for you to see the confidence interval for, let's say, you are interested in beta node. That's nothing but b naught minus margin of error, comma, b naught plus margin of error. See? The confidence interval for beta 1 in a similar fashion. See, estimate is b1 minus margin of error, comma, b1 plus margin of error. Most of these are done by our program. We don't do anything by hand, but we have to get the idea what's going on behind this. See, if you for anything, you can talk about this one for anything. Down the road, that you will be surprised. Even you can remember we talk about that pre-f sum of squared error. Everything gonna change from sample to sample. Those ones also distributed according to another distribution. That's why statistics and data analysis is a little bit heavier at that stage. because we again sum of squared error. Again, we're going to say it's a random variable distributed according to certain distribution. Mean squared error, everything that's found in that statistics in this universe can be distributed, the model with the distributions. Okay, that's the kind of a discussion they are trying to build up over here. Okay, let's get into this book and then see what they're trying to say. That's the same thing. I gave like a kind of like a synopsis, and then I gave everything. It's up. Okay. In the previous chapter, we developed a confidence interval, estimating the error in an estimate. See? In the previous chapter, we developed the concept of sampling distribution. That the same thing I mentioned. When we conduct a study, we collect a sample of data, randomly sampled from the some population. Based on the sample, we calculate the statistics, such as the mean of quantitative variable. We use this mean as an estimate of the population mean. See, that's exactly what I was talking about. Sample mean is an estimate for the population mean. This sample mean is y bar, population mean is mu. Sampling distribution help us to put the sample mean, the one we can calculate, the only one we can calculate, because it's based on our observed sample, into the context of other means that could have resulted if, okay, had we chosen different random samples. See, that's exactly what I was talking about. See, sampling distribution help us to see sampling distributions. Distribution for let's say for a y bar helps us to put this sample mean, the one we calculate, into the context of other means that could have results. Other means also. Why you can only think about this mean? That's why the people, the thinkers, the people who can think deeply, they were thinking, why only that this mean? What would have happened that if it had been coming from a different sample? You were thinking about that based on your sample. Let's say this is your sample. They were thinking that had this had been coming from a different sample, how it looks like. It's different. That they were giving like a space for us to think about in the expanded way. That means they will not rely only on the sample that you have, not only on that one. What would happen that if, like a job, that if you go to one job, they were thinking like that, if, what's going to happen, how much salary, or that, how could I'm going to get a promotion and everything, that if I go to a different job, like that. The same pattern, same thing. If you had if you had got another sample like that, how it looks like. That's, see, this is a sample that this is a sim sample. See, those are not the real sample. These are observed sample. See, that's what they say over here. See, into the context of the other mean that could have resulted. That could have resulted. If we had chosen different random sample, this would have been resulted too. You don't know. See, that's why we're gonna go to the sampling distribution. See, if the sampling distribution is spread out, then we know that our particular estimate could be off by quite a bit. But if the sampling distribution is narrow, we can be sure that our estimate is fairly close to the true population mean. You know this discussion we had that one. That means that what they are trying to say over here with regard to that one. So they say that too much spread out over here, like that. This is your population mean at the center. See, that's the population mean, which is denoted by mu. See, sorry, I'm gonna say sampling. It's not the right one. Okay, sorry, that I'm gonna say mean of the sampling distribution. I'm talking about the sampling distribution. Sampling distribution is nothing but the distribution of y bar, in this case estimate, not y bar. Why y bar distributed? Because we had that discussion earlier that you were thinking that your sample means are coming from different samples. Now you're gonna say it's mean. You can remember its mean is denoted by mu y bar. Mu y bar same as the population mean. And then you pick another value. This is your observed value. See, y bar. Let's say this is observed value. See, observed y bar. This is observed value. Let's say that thumb length you observed from your sample, it's going to be a certain value. Let's say that thumb length example, how much was that mean? we can remember now. 60.1, sorry, 60.1. 60.1 millimeters. You know that. But you don't know about this guy. No, this guy you don't know. This guy you don't know. This guy you know. Then I want to know that your true population mean, this true value and observed value, how differ from each other, which is called the error. That's the error. As I mentioned earlier, it can go up to a certain maximum value later on in order to construct the confidence interval. But at this stage, at least this error. See, if you have the very highly spread out, see, heavily spread out distribution, there's a chance that this gap gonna be larger. See, it's not a good way of doing something. See, if you are that have a different kind of a distribution in which that more or pretty much all your data, all your the thumb means clustered around its mean. Clustered around means there's a high chance that this mu and your observed value get has a very the mean and the sample mean and the population mean have like a very small gap, which is called the error. Error is smaller. See, that's why this is. It's very close to the true mean. See, okay. See, that's error is so low. See, that's why they say the sampling help us to this one. Estimate could be off by quite a bit, but if the sampling distribution is narrow, we can be sure that our estimate is fairly close to the true population. It's very fairly close to the true population. My observed mean is very fairly close to the population mean if this is very narrow. See, I mean, like if it's the most of the data being clustered around the sample mean. Confidence interval lets us build on this logic to quantify how far off our estimate might be. See, that's why they say. They're trying to quantify and say how much your estimate would be off from your parameter based on the characteristics of sampling distribution. Instead of just a qualitative statement of how much fluctuation there might be in our estimate, confidence interval let us say things like our estimate of the true mean, which is 60.1 millimeter. See? But we can say that 95% confidence that the true mean is somewhere between this and that. See, this and that. This and that. How do you got that one? See, that's what they are trying to say. That then instead of that telling that my mean, see, my mean is close to this one. See, look at that. The error is how much that they are off from the estimate means the error. Error means like the difference between the population means and the sample mean. Sample means like I'm referring here, keep in mind. When we have a sample, you might otherwise get confused here. Sample means are if there are so many sample means, why you call the which sample mean I'm referring to. Always when I say the sample mean, I'm referring to the observed sample mean if I give the number. If the number is available, that's only for the observed sample mean. If numbers are not available, that's for the various sample means. This is based on the observed one, the same kind, but this is the only one being observed. These are the one being simulated or bootstrapped. These are bootstrapped. These are being generated, simulated. This is not generated. This is my true value based on my sample. Then I'm going to see how far this is off from that one. That means my error from the population mean. See, that's why they say that this one and say that instead of telling that my true mean, see, our estimate of the true mean is 60 millimeters. See, my true mean. I mean, like I'm thinking about telling no. If I know that 60.1 for y bar, I can make an inference or conclusion. And my true mean also 60.1. 60.1, but we can say with the 95 confidence that the true mean is somewhere between this one. See, that's what they say. Rather than they say our estimate of the true mean is this one, But instead of the estimate gonna be 60.1, I can say I'm confident, 95% confident. See, that the true mean is somewhere between these two. Not the estimate, okay? They talk the other way around, okay? When it's come to the point estimate, you're gonna talk about, see, point estimate, see, point estimate for the population mean, which is mu, is y bar, which is 60.1. That's the point estimate. Point estimate for the population mean mu is 6 y bar, which is 60.1. Rather than that, they talk about just that point estimate. Okay, it's a point estimate. Estimate or point estimate, as I mentioned, just one estimate. You can say that I'm 95% confident that true mean gonna be somewhere here. See. Then you're gonna say 95% confident that the true mean means population mean, which is mu, okay, mu lies, see, is somewhere between these two values. Let's see how we got those two values. The true mean is somewhere between 58.72 and 61.50 and 61.52. See, between those two numbers, 58.72 and 61. See, this one. Later on, they talk about the probability. I come to that one. Okay, so that's what they were telling over here. See, true mean not gonna be x bar y bar. True mean, your true mean. See, your true mean will be from 58.72 to 61.52. But your point estimate is somewhere. You have a point estimate. See, y bar also 60.1. That's point estimate. These are called the interval estimate. Interval estimate. This is point estimate of mu. This is interval estimate of mu. See? How do you get the 61.57? Now you know. How do you get? This is nothing but, you can remember that's the lower bound. Lower bound you get by y bar plus margin of error. How do you get this one? This is upper bound, UB. This is a lower bound, you got it by how? By y bar plus margin of error. Do I know the margin of error? I know y bar. We're going to learn how to get the margin of error later. That for time being, they say that, okay, that's a kind of like a giving and like a idea how to express that one. Instead of telling that, okay, mu is equals to 60.1, you can say my population mean should be that base estimate for this one. I can say my true mean should be somewhere in between these two. That's a good way to express that one. You see, you are interested in true mean. You are looking for an estimate for that one. You say that your estimate gonna be with range having like a lower bound of 58.72 and upper bound of 61.57. That interval is called the interval estimate. See, in another way, that if you write that one with that the notation that we were talking about here, the confidence interval of mu is between 58.72 to 61.52. See, like that. That's the interval. then your true mean also in somewhere in the middle, see, 60.1, we can remember, see, 60.1, that's your true, see, that's your point estimate. This is the interval estimate. Where's the true mean? You don't know true mean, that's why you are trying to estimate. That's why you are trying to estimate. But you, this time you say, I'm gonna do this one with a 95% confident. Where this 95% confident gonna fit in into? They say this 95% confident is expressed like this way. See, if you have something like this, see, this and this, you see, this lower bound and upper bound. This area is the 0.95. That's the 95%. That's called confidence region. Anything fall into that region, we call the confidence region. Then this value, see, then you have a here 58.72. Here you have a 61.52. This is your Y bar, see? Y bar may be 58.72. Y bar may be 61.52. And would that be, what's that for? That is for the confidence interval for, or the interval estimate for mu. Interval estimate for mu with a confidence of 95% confident, your interval will contain your population mean. That's what they say. They are looking for your mean within this interval, where is your mu. See, they say this is the interval for mu. This is the lower bound, upper bound. This is the lower bound for mu. Mu has been expressed in terms of y bars. There are two y bars, lower bound y bar, upper bound y bar. How do you get that one? By adding the point estimate y bar plus the margin of error. We're going to talk about that one systematically. Okay, that's what they say here. See, note that this doesn't mean that the probability, see, true mean. This doesn't mean that the probability true mean being between this one is 0.5. Technically, what it means that true mean will be contained within the confidence interval for 95 random sample that you put. This is not an easy distinction to understand. So don't worry. If it seems obtuse, just keep in mind as you go. Don't worry about that one too much. And then I mentioned that, okay, this as like, okay, 95% area will. See, when you are confident that these two values going to be within your one, you are 95% confident. That's the 95% probability. See, 95% chance. There's a 95% chance that your true mean going to be between these two. That's what they're trying to say. Okay. The basic idea behind this one. Okay. So the basic idea behind confidence interval, the basic logic behind confidence interval developed in a previous chapter, but it's a hard concept to understand. So it's worth reviving it again. Let's start with the idea that the mean we observe. See, that's the same thing that they were talking about. Okay. So that's the same thing that I mentioned over here. So see, that's the same thing. You go and check with the one certain population. You build up simulated means from another DGB. You simulated from this guy. Okay, you can remember with the mean of 57. Mean of 57 and sigma this one. Okay, you try another one with the mean of 63 and sigma of, that's the same thing. And then you drew your histogram like this. Okay, this is your histogram based on your mean. See, you calculated its mean center, which is y bar 60.1. See, okay, now you are trying to put all the pieces together. See, if you put all these pieces together, you can see this is what exactly margin of error. Margin of error is nothing but the maximum error going from this mean to another mean of another distribution, the maximum place. But that mean is nothing but the mean of that particular distribution. See, this is the other distribution, particular distributions mean. See, so this discussion, this is my sample distribution. Sample distribution means my histogram. This is my histogram. This is based on that another distribution with a different mean. See, they use the different mean, different population mean, and with that one they generated. Then they saw that one. There's some, see, distribution like this. See, this one they see this one, the possible distribution 157. Sorry, here with the 63, the mean of 63, population mean of 63 looks like this. Population mean with the distribution with 57 look like this. See, they on both sides. They would not look at their mean. See, here mean. This is my mean, my sample mean. Their population mean. This is sample mean. They see far away. See, far away. It's the huge gap. The error huge, massive. You cannot get the massive error. You have to that put a cap on that one. Then you can go certain maximum value only. After certain maximum value, there you cannot take into account the distribution that come out of the bound, out of those two lower bound and upper bound. See, you can think about, oh, I can get another distribution somewhere here, and then think about its mean gonna be best fit for my distribution, my mean. See, this is the estimate. See, that's estimate value is 60.1. But if you go to 60.1 and 63, it's a large gap. It's not it's very high error. See, that's why they are trying to minimize that. How far you can go in order to generate this confidence interval. See, that's the max you can go. The error can be either you can pick a certain distribution with the 61 or somewhere here. But somewhere here means that's the gap between this mean and the mean of the population mean. It's a population mean, sample mean. The gap, that gap, maximum gap, as I said earlier, the gap between population mean and sample mean called the error. Error when you maximize error, see, maximize error, see, that's called them, see, error. When you go to the maximum error, I put the absolute value to say that you can subtract either way y bar minus mu or mu minus y bar, but its maximum value, this maximum, see, is the error. It has to be maximized. That maximum value called the margin of error. How could you gonna determine the maximum value? It's based on that how much confidence that you have over there. You say that your confidence is 95%. If your confidence is 95%, okay, then you're gonna have your the distribution with the mean of 60.1 here, and then the margin of error being given by this way. So that your 65%, 95% gonna be within this one. See, that's what they explain over here. At the margin of error to the sample, you see, how do you go? If you know the size of the margin of error, how would we find the upper bound? We just mentioned that upper bound is nothing but by adding to the sample mean. If you know the margin of error, if you add that to that sample mean or that estimate, see, we just add the margin of error to the sample mean to get the upper bound. How do you get the lower bound? We would subtract the margin of error from the sample mean. See, so lower bound and upper bound make up the 95% confidence interval. How do you get that one? It's based on the how much gonna be within that, how much your confidence would be. If you go for the 90%, it's different bounds you're gonna have, and the upper bound and lower bound are completely determined by those. Okay, let's say that with this one, see, you can remember this one. See, that's exactly what I showed you earlier. You go to this one. You go to this one, you know how to get this one for the sample. This is a sample distribution. This is the sampling distribution based on the simulated sampling distribution. You know this is the code. That's the same code I show over here, how to get the histogram. Simulated sampling distribution of margin means do this 1,000 times, you're going to get the mean. It has been generated from the normal distribution, assuming that all the data is coming from a bell-shaped distribution. You extract 157 data points from that one, and then in order to extract from that particular distribution, you have to put the mean, because that's how it works. You have to give the mean of that normal distribution. It's nothing but the mean of our sample. Mean of sample is this, the mean of sample. This is a mean of standard deviation. That would give you the all the values. How do you get the thumb stat? By running the favorite statistics for the thumb lengths, data fingers, and you go to GF histogram for the means. Data is sim STOA, and this is the labels. Simulated distribution of this one is the link to distribution. If you want to put like a overlay smooth curve on top of that one, you can say I need the normal distribution. You can give a color. You have to give the parameters. The parameters means mean of this one mean. You go to the simulator sum of SMS, sim SDOA. Go inside that one. You go to the mean. You're gonna find the mean of mean. Those means, okay. The variable, my variable is not the original data, okay? Not the original data. This is the mean. I'm gonna draw the based on the mean. My histogram for the mean, okay, not for the thumb length. Thumb means. Because of that, you have to go to this data set, data frame. You have to go to the variable and then find the mean of that variable. That means you are looking for the mean of mean. You know, we had this discussion. In a similar fashion, you can have the standard deviation of this one. And then you can rearrange. Look at how we're going to do that. Arrange that one and then simulate this one and the descending order or ascending order. Okay, let's say you're going to arrange this one ascending order from the lowest value to the, I'm talking about this data, means, okay, there are 1,000 means. You're going to arrange the lowest to the highest. And if you get the first 25th one, this means go to the 25th one because we are looking for the 95%. As a 95 means like if you have 100, you're going to go to the 2.5 on this side, 2.5 that other side, 2.5 on the other tail. But here, if you have 1,000, you can go to this one. See, 1,000 is 1,000. You have to go to the first 25th one. That's called the lower bound. And you go to 97th entry in that ordered data set. You go to the upper bound and then go to the 97th data point. You read it. That's called the lower bound. That's called the upper bound. It's called the lower bound. That's a one way of getting this one. See, you based on the simulated data. See, then you might be thinking, where's the margin of error? No, margin of error doesn't come into the picture when you do get the standard this stuff in this format. You don't need the standard the margin of error. You simply go and read 25th entry on this side and 975th entry. That would be my confidence interval. Everything in between very much that I mean like can be considered as like a very viable that and then very valuable that the data points, all of that, not the point estimate for the population means. See, we don't need that, and that's another way of getting this done. We can come to that one, but here that's what they are trying to do. See, so 20. This time since you have a 25 is the 25.5 hundredth of the 1,000. I say, why are they interested in the lowest and the highest 25 means? See, that's exactly what we were doing over here. So what we're gonna do, you go to the data set, see, your simulated data, this is exactly this one. You generated the data, the means, the data of all these, and then you're gonna arrange that. And you go to the 25th one, is nothing but that's the 2.5 because I'm looking for 95% confidence interval. 95 confidence interval, as I mentioned over here. See? If you are confident that 95% of chance that your population mean will within this one is all that confidence interval. See, that's how that we can get that lower bound and upper bound. In order to get that one, you can see you're going to arrange from the lowest value to the upper value. This is this cut point. This cut value is nothing but the 2.5 fifth. See, then the rest 5% being left over to 2.5% on this side and 2.5% on that side. If you rearrange that one, this entry is going to be what? For the 1000 data points, 2.5% out of 1000 is what? See, 2.5% divided by 100 times 1000. See, 1, 2, 1, 2, and just 2.5 times 10, which is 25th entry. That's how you get the 25th. The other side, when it's come to this one, it's going to be what? 97.5% out of. How do you get that 95%? Up to this point, how much the area? How much the area? 95 plus 2.5%, which is 97.5%. 97 points out of 1000 is 97.5%. Mean divided by 100, you know that for the 1000. So, and you're going to multiply 975 times 10, 975th. So see, so 25th entry and the 95th entry, 975th entries are the lower and upper bound of your confidence interval. See, you don't need the margin of error in that discussion. No, you don't need. It is built up through the margin of error, but you don't need. See, if you do numerically, you don't need. See, you don't need. Sorry. See, that means that you rearrange that one. You're going to arrange and put it back into the same data frame, and you're going to say this is the entry. See, 25th entry, 97th entry. That entry would be your lower bound. This entry would be your upper bound. That's the confidence interval for that one. We didn't use that margin of error. We simply say that everything, you know that margin of error is already embedded. How do you get this cut value? Based on margin of error. See, margin of error in millimeters. See, margin of error. See, here it's already margin of error over there. See, to find the margin of error, let's find the range within the which 95 sample means would lie. Assuming that mu is 60.1, to find this range, we need to find the point below which 2.5% of simulated sample means failed, and the point above which 2.5 simulated sample means failed. A simple way to do this is just to arrange 1000 simulated means in order. Given that we simulated 1000 means, we know that the lowest 25 means will be below the 2.5% cutoff, and the highest 25 means will be above the 2.5% cutoff. Those two cutoffs are located right at the lower bound and upper bound of the confidence interval. See, that's what they say. See, this one. And they're looking for the mean, and then they do this one. See, 975 or 1000 minus 25. That's the same thing. So in this one, see, if you go ahead and look at for this one is the margin of error. Which one is margin of error? See, margin of error means that cutoff point to the mean to the cutoff value. See, it's the mean. Your mean to the cutoff value. See, cutoff value. If you get the cutoff value and then find that margin of error, they go other way around. Now you go other way around here. Here, without using the margin of error, you found the confidence interval. The margin of error means here nothing but, as I said earlier, we are planning to do margin of error. See, you get the confidence interval by doing that one, but margin of error not appear over there. How do you get the margin of error now? You get the margin of error by getting that lower bound. See, lower bound, look at the margin of error is nothing but, if you go to over here, see, if I'm going to write this one, okay, I'm going to write this one. I'm going to say my confidence interval of mu is you can do this one in two ways: y bar minus margin of error, y bar plus margin of error. This one I'm going to call lower bound. This one I'm going to call upper bound. I'm going to say, therefore, lower bound means y bar minus margin of error. See, that means your margin of error is nothing but what? Y bar minus lower bound. See, lower bound. See? Do you know lower bound? Yes. You know y bar? Yes. How do you find the lower bound? Through the simulated process. That's what we are trying to explain, okay? And the other one, upper bound, y bar plus margin of error. Do you know margin of error again? Yes, margin of error, if you're going to take to the other side, upper bound minus y bar. Look at another way to get it. So if I put this both together here in this picture, this is my y bar, this is my sampling distribution. This is my y bar as well. This is my observed y bar, okay? I'm going to put O, 60.1. See, observed y bar, okay? Then you can remember, see, you can remember margin of error is nothing but upper bound. This is nothing but, this is nothing but upper bound. This is nothing but lower bound. This is nothing but 2.5%. This area is nothing but 2.5%. This middle area is 95%. 95%. See? Then this gap, see? Look at the first one, from this one, from this one, from this one. Look at from this one. Margin of error means y bar minus LB. Y bar here means all the time the observed value, okay? Except for that, if you go with the number, y bar minus LB, see? Y bar minus LB is my margin of error. Y upper bound, go to this one. Upper bound minus margin of error, y bar. This one again, margin of error, see? And together, that's the confidence interval of mu. See? Lower bound to upper bound. If they ask how to get the lower bound and upper bound, you know how to get it. If they want to find that margin of error, you know how to get it. See? That's how the margin of error being that display on the graph. It's nothing but y bar minus the lower bound. Can you find the lower bound? Yes, you can find the lower bound. Let's say in this example, what would that be? Arrange. Okay, we already simulated data. Okay, this is how we did this one. See, it's already set up. Same, do this 1000 mean, R norm 157 mean is thumbstat mean, and then this one. Okay, you know how we did this one. Okay, so I'm gonna put this one just in case. And then how do you arrange this one? See, you can arrange that one ascending order. I'm here, I'm here. Arrange sim STM descent mean. See, that's how you're gonna do that one in a, see, ascending node, descending node. See, descending node. See, go from the lowest to the highest to the lowest. See, you're gonna say arrange. Okay, who will be arranged? Arrange the data sim COM, comma descending order. What's descending order mean? Mean is a variable. Let close it. Okay. Then print 6 lines of STM now. Head. See. They were in the descending order. See, largest to the see, they started from the largest one, going to the see, 62, 62, and keep going all the way to the lowest value. See, 62, like that. See, but this is simulated. Okay, simulated because of simulation. They're not going to be same as what you see over here. And then you go to the tail part, the last one, and see the tail and see this one and see. Last 6 entries, the thousandth one, see, smallest one, see. Notice that we mean a descending order, so you can go down the column label means the numbers get smaller. See, if you want to find the cutoff point to the highest 2.5% of the distribution, we simply need to identify the 25th mean from the top. We will call this the upper cutoff. To find the lower cutoff, we took the 25th mean from the bottom. See, that's what they say. See, you go to see the 25th one. We have 1000 means in our sample. Which of these represent the lower cutoff 25th? Lower cutoff. See, lower cutoff. See, because of the way that they arrange, because they arrange lowest to the okay. They arrange lowest to the highest. Sorry, I'm sorry. Highest to the lowest. Okay, the descending order. Highest to the lowest. Highest to the lowest. But if they need the 1000 means of sample, then lower cutoff for the 25th mean from the bottom of the vector. See, it's this one, 975. See, so that means that 975, the 975th mean gonna be this one. It's the other way around because they were arranging the largest. They were arranging this way. Okay. When I wrote that one, I was thinking this way. Okay. To make it, I'm gonna make it clear. If you arrange your data, see, they go from this side, see, because they go from the larger value on this side, descending order, larger value, largest one to smallest one. That means when you draw the picture, they were thinking about, talking about reading from this side to that side, larger value to smaller value. Okay, I want to make it very clear. If you make this one false, okay, instead of this one, you can get this one what? This one, the value, see, descending order. Can you remember that instead of get that one descending, if you want, you can get the ascending order. See? How do you get the ascending order? Can you remember? You make it like a true or false, no? Can you remember? Make it true or false. See, if it is false, that means it's going to go ascending order. Okay. Let's say that if you don't put anything over here, if you arrange, what's going to happen? Okay. I'm going to show you something to see. Don't put anything here. So arrange. See what happened? See, if you don't say anything, but you just see 61, 59, 61. See, just the mean. See, just arrange only. There's nothing order. See, 61. See, 60, 60, 60, 60. I'm gonna run this one again one more time. Okay, 59, 60. See, mix up. All mix up. Okay. So then you're gonna say descending mean, and then run. See, highest value 62, 62, 61, 58, 58, 57, the lowest value. See, based on whatever the sample already generated. Okay, whatever the sample already generated. See, so when we're gonna get that this one, sorry, look at here. If we have 1,000 means in our example, which of these represent the lower cutoff 25th mean? Lower cutoff even by this one. I'm talking about in this picture. Again, I go with this one. See, lower cutoff is this guy. Lower cutoff is this guy. Since you are reading from this side, highest to the lowest is going to be 975th mean. But if you go to the upper cutoff value, see, upper cutoff value is the first 25th one you're going to meet from this side. See, that 25th mean. And the gap C is always our observed mean, and the lower cutoff or upper cutoff, that gap is called the margin of error. See, when I wrote over here, I mentioned lower bound means go from, I'm reading from lowest to the highest, not to the highest to the lowest. So you read from this side. You come from this side, you take the 25th entry, which is the cutoff value, you read that one, and you're going to say that's the lower bound, then keep going to 975th one, and you're going to call that one, see, the upper bound. But they put the upper bound, they flip that one, okay, they do the other way around. See, upper bound is given by, sorry, see, lower bound is given by this one, or this one, that's the same thing, 1000 minus 25. Upper bound is given by, do they have one? Upper bound is given by 25th one. No, this is the lowest and highest 25 minutes. That one, they were not talking about on this. They talk about only the lower cutoff value only. But in our case, lower cutoff, there one lower cutoff value is this one. Upper cutoff value is this. Okay. So then we got this one. Okay, then tail, and then that one, and then that's why they see. We can use the value in R code to find the 25th mean from the top. See, 25th mean from the top using this one. But this is the upper cutoff value. Upper cutoff value here, because they read from this side. Okay. Then for the upper cutoff value, the way that I put the 975, thinking that I have arranged the data in lowest to the highest. They are highest to the lowest. Okay. It depends on that what you have done. Okay. Type this code to find the lower cutoff. See, and the upper cutoff 975. See, so they say. Okay. So if you go to that one and the mean in that data set, see, sorry, this one, print the 25th mean, see, lower cutoff and the upper cutoff. 975. Type in code to find this one. Let's see what it. See. It's not type in the code to find the, I think they made a mistake over here. See? Type in the find to find the lower cutoff is the 25th mean. No. That's the upper cutoff. See, it should be consistent with this one. It should be flipped. Go to print the 25th mean. 25th mean is not the lower cutoff, upper cutoff there. I'm talking, see. This is lower cutoff. I think they made a mistake over here. Okay, make sure that, because they are trying to do the exactly the way that I was explaining over here. Explaining me like by thinking that they were arranged not this way. Okay, even though the descent means this is not the right one, because even though I wrote this one, I had something in my head that the lower one should be that this one. This should be fix this one for you to see clearly. But since this is me, this one, I'm gonna fix that one as well. I didn't see that one because it's too close to me. Okay, that means that if you arrange in descending order, the lower bound is taken by 975th entry, and upper bound is obtained by the 25th entry. Whether you are on this, you are on like this, your data y bar, you read from here. See, you read this way. See, highest. See the lowest y bar. Here you have the highest y bar. Highest y bar. So because of that, if you got the first 25th one on this, that the ordered data set, ordered means you're gonna get the cutoff value for upper bound, and again you go over there, you get the lower bound. Okay, so it should be like that, 975 and 25, lower and upper. But this is not consistent, because we say that lower bound is 975th mean, upper bound is 25th mean, but later on again they say 25th is lower cutoff. No, 25th is upper cutoff. Okay. Anyhow, by looking at numbers, you can figure out that. See, 61 this one. Okay, I think it's a mistake. It should be upper cutoff 25th mean, lower cutoff 975 mean, because they were arranged in descending order. Okay, right, that's why. Okay, so see, lower bound, they were talking about the same thing again and again. See, see, let's see that. See, vertical line here. See, just calculate the favorite statistic for this one. That's one. Generate the sample mean. Make a histogram for sampling distribution. Vertical line and this one. Vertical line at this 60.1. See this gap. See, and they were looking for the area. See, greater than that one. That area is how much? See. So you're going to do the same thing for betas too. See, okay, they are trying to do the same thing for that model as well. Okay, let's see this one a little bit clearly. So they try to build up the confidence interval. In order to draw the confidence interval, you need the lower bound and upper bound only. Okay, and how much the confidence? 95% confidence. Okay. Okay, let's go over here. See, we got this one. Simulate a sampling distribution of mean centered at mean. See, sample mean centered at sample mean. Okay, centered at sample mean. You know the reason centered at the sample mean. In the center, when you simulated sampling distribution center, not the sample mean. You know that one, because we put the sample mean because we don't know the population mean. Okay, that's the reason. This is the reason. Okay, this is the reason. So then when you draw that you, according to central limit theorem, we discussed that one the other day, your y bar. You are interested in the mean of the, this is a sampling distribution of y bar. See, sampling distribution of y bar. So then its mean is what? Mu y bar is same as population mean. It since population mean is unavailable, this is a population mean. It's unavailable. unknown. See, it's a sampling distribution mean. Sampling distribution mean. Since this is unknown, we're gonna get the y bar. You go to what? Sample mean. Observed sample mean. I'm sorry. Observed sample mean. Sample mean, which is 60.1. It's centered around that one. That's why it's centered around that one. Okay. And then how much far up you can go, how much far you can go in below is called the upper cutoff value and lower cutoff value for your possible means, possible sample means. Not only this one, not only the observed one, possible sample means to fall within this interval. Those are the possible estimates for the population mean. So this cutoff value, you know how to get this upper bound, you know lower bound how to get, you know now. You get the generate data, you're going to arrange them in descending or ascending order, and then you're going to get the 25th and 971 based on that sample if it is 1000. Or you're going to get the 22.5% one from this side and 2.5% from this side, depend on how you're going to do this one. Okay, it depends on that whether you're going to arrange your means from lowest to the highest or highest to the lowest. Okay, you can easily get this upper bound, lower bound. Match the following label to the corresponding part of the figure. See, A is what? How do you find A? 58.7. 58.7. Lower bound. According to this one, okay? Lower bound. Once you run this one, you get the lower bound. See? 58, but not the upper bound. Okay, upper cutoff from 975. See, I got this one. I think, as I said earlier, there's a mix up in this one. This should be switched. Okay, this should be swapped. Upper goes over here, lower goes over here. A 58, upper bound this one. That C is what? C is their gap, either this gap or this gap. See, 60 minus 0.1 minus 50.7. That's the only option being given. Because of that, we're going to pick that. If we simulate the sampling distribution of means again, would we get exactly the same number of for the lower and upper cutoff? Why not? No, because simulated involve randomly generated sample, we won't generate exactly the same sample again. But if you simulate a large number of samples, the lower and upper cutoff will be close. See, if you deal with a large number of samples, your upper cutoff and the lower cutoff will be very close to the value that we got from here. Okay, that's what this. Okay, but you need the large number of samples. Now we've provided the code to find the margin of error from the upper cutoff of the cutoff to the mean. Write the code to find the margin of error from the mean to the lower cutoff. They have given, we have provided the code to find the margin of error from the upper cutoff mean. See, upper cutoff mean minus the mean of this one. That's the upper cutoff. You know that. 25 minus, I'm talking about this gap. Upper cutoff minus the mean of the data means. See? Thumbstat mean, okay? Thumbstat mean. That's the mean. This means 60.1, okay? That's the thumbstat mean. But the other way around, if you do this one, with the aid of that upper bound, see? Write the code to find the margin of error from the mean to the lower cutoff with the aid of the lower cutoff. If you go to the lower cutoff, you can remember, see, here with the aid of upper cutoff, how do you find the margin of error? See, if you want to find the margin of error, y bar minus LB. If you want to find the margin of error with the aid of upper bound minus y bar, it's been provided. If you need the margin of error with the aid of lower bound, then you have to find the margin of error, lower bound, upper bound. This one has been minus this one, then other one come first. Okay. Lower bound, you're going to subtract y bar minus mean. So you put the y bar first. So I'm going to this first. And then seeing this one, 970. Right? Okay, whatever, 7, sorry, minus. See, they close. They both are 1.4, 1.4. See, same answer. You should get the same answer. The margin of error, maximum error that can incur, okay, is this one, 1.4, 1.4. We find the margin of error above the mean and below the mean is roughly the same thing. Why do you think the lower and upper cutoff points are approximately the same distance from the mean sampling? Because the sampling distribution of mean is basically symmetrical. So the distance from the middle to the top 2.5% mean is the same as the distance from the middle to the bottom 2.5 means. It's basic. Okay, that's the reason. So we're gonna see. We know from the central limit theorem that the shape of the sampling distribution is approximately normal. See, we know, we discussed that one. That's symmetrical. We can see this in the simulated distribution of mean. There seem to be as many means left of the center as right of the center. Therefore, once we find out where the lower cutoff value is, we know where the upper cutoff point is. Okay. So constructing the confidence interval from the margin of error. See, now with the aid of the margin of error, we are trying to construct the confidence interval if the margin of error has been given. See, we use the simulator sampling distribution centered on the sample mean in order to calculate the margin of error. Now we are trying to margin of error. It is important to remember, however, we are trying to construct the confidence interval with the aid of margin error. Earlier we did this one confidence interval not with the margin of error. We found the margin of error once you have the confidence interval. How do you construct the confidence interval? By simulating and arranging the the descending order, and then you found based on this 1000 sample 25th cutoff value and 97th cutoff value were given. They were the upper and lower bound. That's the confidence interval. Here they were talking about different thing. They were talking about that with the aid of the confidence margin of error. I'm talking about this formula. If you know the margin of error, see this formula. If you know the margin of error, if you know y bar, we know y bar for sure. By subtracting margin of error from y bar and adding my margin of error to y bar, you can easily get the lower bound. Earlier we did the other way around. We found this one straight. Now we're gonna try to get this one through this formula. Okay, that's what they were telling you. With the aid of the margin of error. We use the simulated sampling distribution centered at the sample mean in order to calculate the margin of error. It is important to remember, however, that our real interest is the range of possible population means from which our sample could have been drawn. Yes. Lower bound, upper bound. See, we have margin of error is this gap. Okay. This area is 95%. You know that one. See, in that our distribution. Looking again at the picture we presented earlier, we can see the margin of error 1.4 from the sample mean to each of 2.5 tails is exactly same as distance as from the sample mean to the lower and upper bound of the 95% confidence interval. Yeah, see, same 1.4, 1.4. If we remove the sampling distribution centered around the sample mean from the picture, we can clearly see the margin of error from the lower bound to its upper 2.5% cut ends precisely at the sample mean, and the same distance from the upper bound to its lowest 2.5 cutoff into this one. The key point is this one. If the true population mean was at the lower bound, it means that there's only 2.5% chance that the mean we observed or higher would have occurred and it had been random sample. See? So what they were trying to say over here, see, they say the key point is this one. If the true population mean was at the lower bound, let's say your true mean is lower bound, it means that there is only 2.5 chance that the mean would be observed or higher would have occurred had it been a random sample. See, there's only 2.5% chance that the mean we observed or higher. See, mean we observed or higher. See, from this distribution. If you go to this distribution, see, higher. See, 2.5%. See, it's a 2.5 chance. Chance means that area, this area. See? This area, 2.5% chance. It's a 2.5% chance. This whole thing, 95% chance. See? See? Chance that the mean we observed or higher would have occurred had it been a random sample. And if the true popular mean was at the upper bound, there's only 2.5% chance that the mean we observed or lower would have been drawn by that chance. That means if you assume that your true mean gonna be here and here, if your true mean, we don't know where the true mean is at. In this range, from this lower bound to the upper bound, they were talking about if it is that here, there is a 2.5% chance it's going to be at that point. That's what they say. There's a 2.5% chance it's going to be at this point. See? And altogether that is going to be between this range is how much? 95% chance. That's they are trying to do over here is they're trying to get the cutoff value which fit in into 2.5%. That's what they're trying to do over here. They go with a different route. Okay? That's what they're trying to do over here. See? So what they're gonna do, see, they're gonna go ahead and find what would be the area, see, more than this one. See, if that's the case, see, if that's the case, what would be the value here? Cutoff value. They need this cutoff value. See, they're looking for this cutoff value. See, that's why they had, see, 1.5 to 6.1. See, 61.5. See, so what they did was, okay, I'm going to explain this one. You see, we constructed 95 confidence interval by simulating a sample distribution of 1000. Okay, sorry, based on the simulation, we can say that 95% confidence interval, the range within which we are 95 confidence, the true population mean must be 60 point plus or minus 1.5, because that's how we got this one. Another way to thinking of this is that the range population means which observed mean is considered likely. See, anyhow, that the population mean gonna be between, see, 60.1 plus or minus 1.4. That's how you got this one within this range. See, 58.7 to 61.5. So now they say that we construct a 95% confidence interval by simulating sampling distribution of 1000 means centered at our observed sample mean. But our real question was not about the tails of this distribution, but the tails of the sampling distribution that would be centered on different possible populations. See, they were talking about the tail of the sampling distribution. For example, if our lower boundary of 95% confidence interval is correct, then there would be reason that there would be a less than 2.5% chance of selecting a sample with the mean of as high as 60.1 if the true population mean was this much. So blah, blah, blah. Okay, I'm going to explain this one and condense. Okay, let's use the R to generate the simulation of 1000 means from the sample of 150 drawn randomly from normally distributed population with the mean 58.7. See, we'll continue to use this standard deviation from our sample as an estimate of the population standard deviation. Plot the sampling distribution of means as a histogram and calculate vertical line at the population mean 50 and then at the sample mean this one. What they are trying to say over here, so that let's say that R generates 1000 SAM means from this one, okay, with the sample of 157, assuming that they were normally distributed, with the mean of 58.7, they go to the lower bound. We already found the lower bound. We already found the lower bound. How did you find the lower bound? We found the lower bound in two ways, okay? We are trying to just like a little bit, see, as we say that it is a little excursion to the test our logic, okay? So what they want to do, they go to the lower bound and they're going to draw, see? Sorry, see, 58.7, see? They're going to generate the data from the 58.7, see? Look at, modify this code to generate samples from a population with not this one, not the mean. The standard deviation is the same, okay? Mean 58.7, 58.7. And then make a histogram of sampling distribution. Okay. So we know that when you go to like a GF underscore histogram, okay, of mean, you're gonna do data, gonna be sim em log. That's gonna come from the width date of the low bound row vertical line at the see, vertical line at this one. Then we can get this one. GF line. Set. Remember GV vertical line, V line, x-intercept. Then at which point? Vertical line at the mean of the sampling distribution, which is 58.7, 58.7. And with another vertical line at our observed mean. See, another one. Another one. In the same. Okay, this one. And it's gonna be x-intercept 60.1. Which one is missing? 58.71 we saw. That's the second one. Oh. Yes. This one. This is here, this is here. See? Lower bound sampling distribution of the mean. I draw like a sampling distribution with the aid of the lower bound. With the aid of the lower bound as the mean. See? So 58.7. Now the question is, where does the sample mean fall relative to the highest 2.5% of simulated sample mean? With R, we can see it's going to go to the highest part. In descending order and color, any means higher than 25th simulated means. That means mean greater than, see, this one in a different color. It will also include the sample means as a vertical line. See, sim data arrange, see, descending mean, histogram, mean data, sim data, fill, mean greater than this one. Wins are 100. V line, see, thumbstat mean, see. you run this one, you get, see, true and false. Sample mean 60.1, false right of the upper cutoff of this one. For reason you may not starting to understand, if maybe our DGPC, corresponding sampling distribution, so that their mean is about 1.4. So this gap is like, see, that's why they were trying to say over here. So they're gonna get the, see, 60 to see 7, 8, this one 2 point something, that the gap, see, but the 2.5 coming from which one, see, 2.5, see, coming which is more than, see, not only 2.5, see, your point has to be shifted, see, look at the true part, see. Let's say the question is, where does the sample mean fall? Your sample mean fall relative to where is your sample mean? See, this is your population mean, thinking that your population mean has like a center at the this one. Sorry, your that lower bound of the confidence interval. This is your observed value, 60.1. See, that's why they say, where does the sample mean fall relative to the highest 2.5% simulated sample means? With R, we can sort the scores in descending order and color any mean higher than 25th simulated mean, see, in a different color. We'll also include the sample mean as a vertical line. See, this is sample mean. See, this is my sample mean. This area is the 25th cutoff value. See, this is the cutoff value. See, this is the 25th cutoff value. This is your mean. How do you get the 25th cutoff value? See, that's what they say. This is your, see, this is upper cutoff value. See, upper cutoff value for the 25th data entry here. This color area. This area is 2.5%. But your observed value is lower than that one. See, it's lower than that one. The maximum you can go to this point. That's why they're trying to say. Your that y bar can maximum go here. Maximum go here. See, on this side. In a similar fashion, on this side, you can go maximum to the lower 25th percentile. Sorry, 25th percentile or 2.5% area, that cutoff value on this side. That's the maximum you can go on this side. It's a maximum you can go on that side. So when you come to and reach to this point, 60.1, your observed value is still within that one. See? So for that, because of that reason, that's why they're going to use with the aid of this one. See, 60.1. See, put this one. The same thing that we discussed. The same thing that we discussed earlier. This is for that when it's a null model. Can you remember? Just we predicted our sample mean this one fall right on the upper cutoff of the sampling distribution. See, right on the upper cutoff of the sampling distribution. For reason you may now starting to understand. See, because when it comes to this one. So bottom line, I think that rather than going through this one, what I'm going to do, I'll show you, because I think they were making this one very complicated for no reason. Okay, this is what you have to do. See, on the bootstrapping one. The major thing what I want to tell you over here. Hold on. Yeah. Okay, this is what they're trying to say over here. Okay, that one is not that the bottom line. Okay, this can be put it in 3 ways. Okay, so I think they were trying to this textbook trying to make it everything complicated for no reason. Okay, this is the bottom line. So what we are trying to, okay, I'll show. This is So as I mentioned over here, we are trying to build up the confidence interval in 3 ways. I think they've tried to explain this one not very properly, well not structured. This is not a proper way of explaining this one. They go through the same thing again and again and again and again and try to convince something, but it's not just, see, again they were talking about the same thing again. See why they were so worried about that one. See, so this is the bottom line. What I'm gonna do, I'm gonna show you something over here to make it clear. Okay, this is first one. See, they were just mentioning the same thing. Okay, with the simulation. Okay, we found with the simulation. Okay, see, they were trying to that. Just they're gonna utilize a different mean. You don't need a different mean. You can straight go to your distribution and then talk about that one. That's enough. They go to different distribution and say that go to this side and that side. No, it's not necessary. See, they do the same thing that on this side. See, now they here. See, 60.1, and they're gonna be inside. See, no such thing as a confidence interval in statistics. Yeah, Bootstrap. I see this one. Bootstrap. See, tiny fingers data Bootstrap. Then let's try by reviewing the resample command. See, resample means from this one you're gonna pick numbers. Pick numbers. Those numbers not be the same as that one. This is what I'm trying to say over here. Okay. Okay. There are 3 ways you can get this done. Okay, I'm gonna get you over here. This is one way. I'm going to go to the Bootstrap first. There are 3 ways you can build up the construct the confidence interval. That's the bottom line. Okay. Through that, as I mentioned, without using the margin of error, we're going to get this done. Forget about the margin of error for time being. Otherwise, the way that they describe in this textbook, they messed up everything. Okay. So simply, this is what we're going to do. First method, you go to Bootstrap or simulated. Let's say I'm going to explain this one. Simulated. We did this one earlier. You go and simulate data. See, assuming that your population is normally distributed. From that one, you simulate 157 data points. And you use in order to use the R norm, you need the mean and standard deviation. You get their mean, and you do this 1,000 times. And you can draw the histogram, you can do the labels, you can do the overlay in the distribution. The key part is then you're going to arrange this one in that's it. From here to here, straight to. You're going to arrange this one in descending order. And since you're going to arrange from descending order, you're going to have the smallest one here, the largest one on this side. Because you arrange from the lowest to the highest. So if you read from that 97 fifth, you're going to read from this side. Since you have the highest one in your hand, you're going to read from the top. You're going to read the values from the top, and then you meet the first cutoff value, 25th cutoff value. That's the upper bound. That's a 25th entry. Because 1,000 data points, I show you how we got this one. See how we got the 25th and 975th based on the 2.5, because we are saying that we are 95% confidence. We need the 95% confidence interval. That means we are confident. If you draw the confidence interval, construct the confidence interval based on different samples, at least 95% confidence interval will contain the population mean. That's the rough idea. Okay, that's the idea. Okay, that's what they were trying to say. So because of that, these two would be your upper and lower bound. Let's go to the second method. Second method is bootstrapping. Bootstrap means like rather than thinking that your data coming from another way of that generating data, The bootstrap means that you resample, you recycle your data. You have 157 data points, your data. From that one, you're going to randomly pick some data point. It is not necessary to be that let's say you have a 65, 70, the data values. Sometimes you're going to pick the same value, like the way that they were doing over here. Look at this. This is for the tiny fingers data, see? 56, 60, 61, 63, 64. But when you're going to pick from this one, resample from this one, resample means like with the replacement. You're going to pick one value, you're going to put it back. And then you pick first time 60. Again, you pick the 60. And the 63, 56, 61, 61. That's called the resampling. You see? That's called the bootstrapping. See? You are bootstrapping. When you're going to pick the same thing, you're going to utilize the same sample and recycle it and then pick the numbers from the sample. You're not going to pick another sample. Sorry, you're not going to pick another. Physically, you don't pick a sample. You're going to pick the numbers out of that one. See? Okay. Look at the numbers. They're not necessary to be all the numbers. Okay. Some 157 numbers will be here that since we are doing 157, you're going to resample it, and that's called the bootstrap. Boots STOM, and from that one, if you do the same thing, and if you write this one in descending order, I think again that I have to change that one. If you go to the lower bound, it's a 975th entry, and if you go to the upper bound, it's going to be the 25th entry because this has been arranged in descending order. Or you all the means been arranged in descending order. Okay. I'm going to a little bit clean that. I fixed that one. Let's see. Yeah, I wrote that one. Okay, sorry. So this one is this one. I'm going to say lower bound is 975 entry. Upper bound is okay. So this is that's the lower bound. It's the upper bound. 25th one. So you can go from you get the bootstrap from here. And the third method, we're going to assume that we can get your margin of error. Okay, I'll show you how to do that. So the third method, I'm going to go to third method. Third method we call normally distributed sampling distribution of y bar. Okay, so that means this is how you're going to get the lower bound. In that case, look at how I'm going to get. Okay, I make it easy for you to see this one. You go to y bar minus margin of error. Margin of error is given by ZC. I'll tell you what is ZC. Sigma over square root n. That means since you don't have a sigma is the population mean, what you're going to do, you're going to replace this one with sample standard deviation and this one. This one we're going to say cutoff value, which cutoff value? Lower cutoff value from normal distribution. Actually, we use the standard normal distribution. We have standardized standard normal distribution. See, that's the margin of error. If you want the upper bound, in this setting, you go to y bar plus margin of error, which is y bar plus margin of error is nothing but ZZ over sigma over square root n again. Then y bar plus ZC S over square root n. This one is sample standard deviation. This one is sample size. See? sample size. Okay, so this one is same thing over here. This one are we gonna say upper cutoff value, upper cutoff value. This one is lower 25th cutoff value, 25th cutoff value. Okay, this one upper 2.5 to 2.5. Okay, this one is 97.5th. Okay, cutoff value, percent cutoff value. As a percentage. Okay, as a percentage cutoff value. Okay, you can see here cutoff value. See, that's how you're going to get the upper bound and lower bound. And on the other hand, if I write this on one more time, LB y bar minus ZZ sigma over square root 10 O y bar minus ZZ S over square root 10. This part we're going to call the standard error. Standard error, you can remember that one. Standard error is nothing but standard deviation of the sampling distribution. We did this one earlier. Okay. And the similar fashion upper bound, the same thing, y bar plus CC sigma over square root 10 y bar plus CC S over square root 10. This part is same thing. See, Z coming from, see, ZC values coming from, okay, I would like to call this one ZC, the other one CC star. Okay, for you to make it very clear. Upper one, I can put CC star. Lower one, C. This is what I'm talking about. You go to the Z score, normal distribution. It has like a zero at the center. You know that one. This is a standard normal distribution, not the sampling distribution. I'm not talking about that. A standard normal distribution. And you go over here. This area is 2.5%. Again, this area is 2.5%. In the middle, you have a 95%. You go and get that the inverse value of this one. How do you get that one? I'll show you how to get that one. Okay, you're gonna go and looking for the quantile. This quantile 22.5% quantile. This one 97.5% quantile. How do you get that one? What's the code for that one? You go Q norm and you put the area to the right, which is 0.025. This is area, area to the left, area to the left, area to the left. You know this area, left, area to the left. Okay, this one is area to the left, area to the left. So here, same thing, Q norm. Q stands for the quantile of the normal distribution. You're going to go ahead and put 0.975 as a decimal. See that one again, area to the left. That would give you the cutoff values. That way, cutoff value, you're going to bring it over here, put it back over there. So how do you get this one done? Then lower bound is nothing but, okay, I'm going to write one more time, y bar ZC S over square root 10. The R, you're going to write mean of go to fingers and go to thumb. That's mean. That's y bar minus CC. You have to get Q norm of 0.025 and should be multiplied by standard deviation of go to fingers and go to thumb, okay, and divided by square root of 157. See, 157. That's how you're gonna get that one. That's the code you can use in order to get this. If you do this format in third method, fingers, go to thumb, get the standard deviation. See? Then if you go to the upper bound is y bar plus zc star s over square root 10. This is, so back to this one is zc. This one is zc star. See? So this one is again go to mean of fingers and go to thumb plus critical value or quantile, critical value. So many know this guy. See, quantile. If you want, you can say critical value. Critical value. You say cutoff value. Threshold value. Table value. See, so many names. Table value of C. Okay, of C. That's the same idea. So does with this one. See, lower critical value, lower cutoff value, lower threshold value, lower table value. Pretty much same way you can say upper cutoff value, upper critical value, upper threshold value, upper table value. That's the idea. Now you're gonna say Q norm. You put 0.975 times standard deviation of go to fingers, go to thumb divided by 157. See, if you are using, okay, using that your this this normal distribution. There's three methods we were discussing over here. See, using normal distribution. Now there's another one, because when I go through this one, I can go through in there's detail there and that one. Instead of that one, then later on they go to another method. We're gonna put this one and we can stop and then we can do the rest next time. Called the T distributed. I'm gonna introduce another distribution called T distributed sampling distribution. Distribution of Y bar. Instead of using Z distribution, now they are planning to use something called the T distribution. Okay, T distribution is very similar to C distribution. It's a derivation from the C distribution. Okay, okay. So this can be tackled by something called, its characteristics is degrees of freedom. Degrees of freedom. Okay, freedom. In another way, if D goes to infinity, very large infinity, T distribution becomes Z distribution. Okay, that's the idea. That means they're like a same kind of a Z distribution. Most of the time we are using not the Z but T distribution. But again, in that one, okay, you can do lower bound and upper bound. Okay, lower bound or upper bound. I'm gonna put both at the same time. You go to thumbstat. Same formula. Only difference here, instead of that T, Z, you're gonna have a T. I call this one T star. Okay, this one T. See, this one is 2.5, 2.5%. This one 2.5%, 95% inside. See, your bounds. See, those are the bounds. Okay, thumbstat. Okay, go to thumbstat and go to mean. Plus or minus. Okay, it depends on plus. Okay. Okay, I'm gonna put the plus for the upper bound. That's why I put plus, minus for this one. That's what it means. Okay, I'm gonna say the formula say like this. Okay, thumbstat. You're gonna write QT, quantile of T distribution, 0.025, and degrees of freedom How do you degrees of freedom? N minus 1, which is 157 minus 1, which is 156. You have to provide that one too. Okay. Or that's for the lower bound. If it is upper bound, you put QT 0.975 degrees of freedom, which is 156. Okay, that's why I put the slash. Okay, I wrote both at the same time. And thumbstat, go to thumbstat and go to SD. If you want, you can do like that, or find the SD of the thumb. Okay, either way. And square root, I'm going to write this one in a different way. Square root, go to thumbstat, and go to N. That would give you another way of writing. This is what actually, this is what I wrote on that side. See, lower bound is nothing but y bar minus t, okay, s over square root n. That's what I wrote. Upper bound is nothing but y bar plus t star s over square root 1. Those two are the ones that I wrote on the other page. See, this one. So those are the four they were that so heavily talking about. So basically, in order to write the confidence interval, you can go through this route, see, lower bound, upper bound, see, or this route, okay. And there are other two in the very beginning I did, okay. Simulated, okay. I'm referring to this one, okay. Simulated and this one, Bootstrap, see. If you go through this one, first one is on this page, see, 079, see, 079, page 079, you don't see, 879, okay, 79, okay, then straight go to 79, then this page is, I put the page number for you to see clearly that normally distributed assuming 89, 90 and 91. It's gonna be like the point. I'm gonna write page numbers for you to see clearly all the four methods on this one. If you go to this video, you can see easily. Okay, point, see page 479 pages. Okay, pages 79, that is 78, 79, 78, 79. Not that one. Those are other concepts, but related to this all four methods. One method, one, yeah, here. 89 through 91. Those pages has all four methods. Bootstrap and simulated, bootstrap simulated, normally, distributed, t-distributed. All about the y bar, okay, y bar, okay. And you're gonna write the confidence interval. Confidence interval always nothing but lower bound and upper bound. How do you find the lower bound and upper bound? All these four methods described very clearly, okay. So you can have a look at it, that one, and then get an idea, because in the textbook they messed up. They talk about the same thing again and again and again. It's redundant, plus that they don't do a good job on that explanation. Very confusing. See, for you, for me, okay, I can understand what they were talking about, but with the same context, if I'm trying to explain to you, if you're gonna read, you're never gonna get a clear idea what they're talking about. They messed up. Best thing, we are in the middle of that, finding that the range of estimates for y bar. How do you do that one? Using bootstrap method, simulated method, normally distributed method, and t-distributed. Every method has its own way of doing that one. For instance, in the t-distribution, you can go See, thumbstat plus or minus, minus for that lower bound, and go to QT, quantile of that guy. See, quantile of this one. See, T and T star, those pin. This is the formula. This is the R code. This is the R code. And then you go to this one. These are the R codes, lower and upper bound. And if you go to Bootstrap on page 78, sorry, one, even it says 78, on this one it says 78, okay. You go to this one, you generate a straight, go to this one, see, lower bound. How to get the lower bound? You go and don't worry about the histogram and labels and distribution. Go to that, rearrange them in the descending order and get the lower bound and upper bound. Same thing with the simulators distribution. So I'm going to go through this one in detail again next time too, but you can get started with your doing a homework and everything, because that's the way this has to be done. I think otherwise too much. And then we go through some places and then let's answer. Because they were talking about the same thing again, and upper bound, lower bound, and they draw so many unnecessary that distribution. This is not a proper way of. You don't need this distribution to be. That they were not a part of this one. Okay. Anyhow, that we can get a clear idea about what's going on easily with the way that I'm doing over here, because you don't have to go through this one too much. See, they not see later on they go to the T distribution as well. So see, they jump into the regression model and then try the confidence interval. That's what we are planning to do. As I mentioned that earlier, Y bar comes in the regression models. Okay, that's how we are so much interested in Y bar. You know. Okay. Anyhow, do you guys have any question before I'm gonna let you go? If not, I'm gonna let you go and then see you guys on Thursday. Okay, let's continue same discussion on Thursday. And then okay. Yeah, thank you very much. Have a good night, and then stay safe and be well. And then see you guys on either Thursday or that Wednesday. If you guys have any questions, just email me. That then I can keep that office hours. Okay. Thank you very much. Take care and good night. Okay.